Good morning, dear student, and welcome to this fourth edition of our Numerical Method 2 class. First of all, I would like to apologize because I sent an information according to which I was to attend a virtual meeting. Actually, I logged on and I realized that those who were supposed to meet from 8:30 were the members of the panel. So that's why I asked the class representative to inform you that we can meet. Okay, but those who are not present, this is not a problem because the class is being recorded, so they will watch the video later on. And some will join us in the process because I can see Cindy is also joining us. Those who will be informed, I think, will also join us. Okay, this being said, let us dive straight into the crux of the matter. I will share the window. So we have been talking about Fourier expansion, Fourier series. Okay, so we saw that Fourier series is a series that can be expressed in a particular form. So it's an infinite sum of combination of sine and cosine. Can you see something on your screen? Okay. Okay. Slow.
Yes, you can see now.
So first of all, we talk about Fourier series only for periodic functions. So if you want to expand a function in its Fourier series form, that function first of all has to be a periodic function. That's the first thing. The function has to be periodic, right? And the period is given by p, but in our case, we assume that the period is 2π because of this formula. If you look at the formula, we will see that the interval that we are using the interval negative pi, and you can see that the length of this interval is 2π. So that's why we have this formula. But as I told you, this interval this formula can be generalized to a Fourier series of period, for a periodic function of period t or p. In our case, we call it here p. But generally, the period is denoted by t, capital T or p. But it doesn't matter. If it does not offend anybody. Okay, so if the function is of period 2π, this is the formula for the Fourier series. You see that here we isolate our a0 by 2. That's our first term. And the remaining terms are grouped as a combination of cosine and sine. And the coefficients, the AKs and the BKs, are given by Euler's formula, as you can see here. Okay, so far, yesterday before we parted, we went through this example of the representation of the Fourier expansion of the function f, defined by f of x equal to x by 2 for x in the interval negative pi. And this definition is extended throughout the real line periodically, such that our function remains a periodic function of period 2π. And to do that is easy. You can proceed in a similar manner if you look at this graph. for our case where x is equal to f of x equal to x by 2, okay, over the interval negative pi, you would draw your function. Okay, let me do that. Let me try to draw to show you how this function can be represented periodically. Because when I ask students to represent this function, you give them the function, they are not even able to draw it. You see that you really have a lot of problems with mathematics. Still be passing module for which reason, I don't know. But when you ask a simple task, it's a problem. If I give you that function, if I ask you now to represent this function, this one, defined this way to represent it on the real line, a lot of you will not be able to do it. I'm saying it out of experience. So let me try to do that. Oh, okay. I'm already sharing a different, let me go to the slide because I have a different slide I'm looking at. And I have the impression that you are also watching the same thing, but you don't, it's not in front of your screen. So sorry. Okay, let me share that because I want to draw this function f of x equal to x by 2. Okay, so this function f of x equal to x by 2, which is defined on the interval negative pi. So we are going to extend this periodically. So how does it look like? Really slow, huh? The response is slow. Okay, so okay, let me do this. Let me first write a date here. Today is the 8th. Yeah? 8th. Wow, time is running. Yeah? Hey, time is running like no one's business. So this is our, okay, I can take it this way. This is the origin. Okay, let me put it here. This is the origin, and our function f of x Okay, so that is the function. So meaning that at pi and negative pi, it will be pi by 2, negative pi by 2. So that's the value of the function. So we'll assume that from here to there is exactly pi by 2, this height. Would that be too long? No, I don't think so. I don't think so. So this would be our pi by 2, which is 1 point something, because pi is 3 point. We divide by 2, it will be 1 point, around 1.6, something like that. Okay, so this will be our pi by 2. Okay, let me do this. I hope it does not hurt anybody. It does not hurt your feeling. I hope it does not hurt. Ooh. Now it can hurt, eh? Because it was not straight. Oh no, this is not nice. Okay, now it is nice. This is nice. No, this one is not nice. Yes, that one is nice. No. Okay, so as I was saying, I will assume that this is pi by 2. I'm free. I'm free to decide it. When your father called you Emmanuel or whatsoever, he was free. He didn't ask my permission. He just say, okay, guy, you will be called Emmanuel. No. Okay. We continue. Life continues. We are here to do nice stuff. Okay, so I continue. So this one, I call it pi by 2. Obviously, this will be negative pi by 2. I can put it wherever I want. I'm free to do that. Nah? It should not hurt the feeling of anybody. It should not hurt anybody. Okay, now I will change the scale a bit because I want more. Okay, so I will decide that this. Okay, let me do this. Let me do this. It will really help me if I do that. Yeah. But I hope it will not hurt anybody. Okay, so I will decide that this length, this is our pi by 2, this one. So I put this one here, that's pi by 2. Okay, so if that is pi by 2, I can do the same, put it there like this. Use that same length like that. You see? Anyway, you waste our time, so I don't really need to be carrying this all over because at least, yeah, it helps a bit in terms of measurement. It helps a bit, just a bit, a little bit. It helps, man. If you yell at me, I also yell at you. Okay, so yeah, you see, like that. But it's a bit, it's a waste of time anyway. We are wasting, but not that. Anyway, I'm not taking it to somewhere. I'm not going to. taking this to an exposition. I would just put it like that, like that, like that. I've just approximately. So I would just do that all over. Okay, good. Now this is, I say pi by 2. Oh, was I even wise when I say pi by 2? Okay, I will say that this is pi. Instead of pi by 2, I will scale this to pi. Just for you to have an idea. It can still be pi by 2, and this will be pi, but you see that it will go like this. You see what I mean? Okay, let me explain. I will explain, but I will change that scaling. I will change it. I don't want that. Okay, if this is pi by 2, this will be our pi here, and this will be negative pi. If you understand what I'm trying to say. But now, our point, the first this function, we start from here and end there, you see? That's just one, and then I will translate throughout. The scaling is not nice. So that's why instead of putting that here, okay, let me do that. So the first function, because remember that at negative pi by 2, I'll have to divide it by 2, so it will be this one. So the function will be here. It will start here, it will go through 0, and it will continue here, and at pi, you see, it will be like this. And I will repeat, but you see that this is it's too big. It's too big. And I will not be able to represent enough functions. So I want to reduce that so that I can represent at least a lot more. See, it will be like this, and then I will translate this like that, to make it periodic. Good, so that is a function. And now what I would do, normally I'm supposed to do this. For the next interval, that will be from pi to 2 pi, right? Okay, let me put 2 pi first. If you don't have any problem with that. Okay, so that next thing, this will be 2 pi. 2 pi will be here, 2 pi. And then the next time, 3 pi will be somewhere here. So we have pi, 2 pi, 3 pi, and here we have negative 2 pi here. Now, negative 3 pi will be far somewhere there. So you see that I will not be able to represent enough, right? But if I reduce it here, I'll be able to represent a lot more functions. So I do this. Bam, bam. Oh no, no, you, man. Not you. I'm pissed off. Why are you copying what I'm... No, I didn't ask you to do that. I'm not happy. All right, so this is what I want. I want this one. Okay, let's see if you will copy what I want. Pin. Oh no, I'm not happy. Anyway. Okay, so it will be something like this here at pi. Okay, it will start from here and it will continue. That will be from, he also even copied pi. Yeah, this is terrible. Oh, no, man, but that's not what I want. He copy and copy what I don't want. All these things. I don't want all these. I don't want all this. No, man, that's not what I want. Okay, now I can take it back again. Okay, so something like this. You see now that the scaling is not good, because normally it is supposed to be, if I shift it by, so this should be from what? If I 0, I shift it by 2 pi, so 0 will be at 2 pi, so it's supposed to be here. right, like that. And now it will be from pi to 3 pi. So yeah, so it should be like this. But you can see that my scaling here, they are not good. So I cannot really use this because of the scaling. My scaling is not good. Okay, but let me give you an idea. That's why I wanted. Okay, so you take this, you just translate. You just translate like that. So meaning that this, you shift this by 1 because the period is 2 pi, right? So from negative pi to that. So I add 2 pi to this one, to each point. If I add 2 pi to this point, you see that it comes here at pi. And if I add 2 pi to this, it will be there. So this 0 should be here. So actually what it has to be, it should be like this. It should start like that from pi, it goes to 2 pi, and it stops at 3 pi like this. Yeah, it's exactly like this. So it's supposed to be like this. But you can see that with the scaling, it's not exactly that. Okay, so that's what we are supposed to do periodically. Now on the other side, here, we will do the same thing. You shift this by 2 pi, so this will be negative 2 pi, so negative 2 pi will be here. And you will go from negative 2 pi to pi. So we have this. Okay, but let me, so it will be something like this. And you can see that here you have a discontinuity here. Oh. Oh, anyway, here you have a discontinuity that unfortunately like this. Oh. Okay, those are point of discontinuity. So it should be like that. Translate. You draw in the interval negative pi pi, and then you translate it throughout. So this is our periodic function. So for good scaling, I was supposed to reduce it so that you have more graph. Okay, so that's how you represent it. I don't think it was a waste of time, but at least it gives you an idea of how to do that. So that's how you represent the function. You extend it periodically throughout the line. And it's similar to what I show you on the slide. Okay, so this is what we did yesterday. Now let us tackle a new problem. I will come back to this slide. Let me go back to our notes. Okay, so this is what we got yesterday. Now, is there any new problem? What else were we supposed? Okay, now let us look at this. Here you have the graph of some approximation of this series, because remember it's a series. But you can never represent a series, right? Because a series has an infinite number of terms. As you can see here, it goes to infinity. But we cannot plot to infinity. You have to truncate or to chop. You have to chop it somewhere. You have to truncate and plot an approximation of this series. For instance, you can take 100 terms. 100 will be good enough to approximate that. But here we are giving you a few, right? The first few terms for you to have a feel of what it will look like. So we will be computing partial sum. What is a partial sum? When you have a series, it runs from maybe 1 to infinity. Partial sum means that you take n terms, right? So we fix n. You can see here we fix n, and we define S sub n, which is the sum when k runs from 1 to n. So we call that partial sum, right? It's a partial sum. Now, if you take n equal to 2, meaning that you will take k equal to 0, k equal to 1, k equal to 2, sum them up, add to a0 by 2, plot it, right? So now if you look at the graph, you see that we have three partial sums that are plotted. You have S2, S3, S4. And they are given here if you look at the legend. The legend is given. Okay, let me put 200%. Okay, if we take 200%, if I put, okay. Now, you can see that this one, the graph in blue, this one, the blue graph, this one, is S2. Obviously, the first one, the one in red, I'm sorry, the one in, not red, sorry, in black, this one, this is the original function, x by 2. If you recall what I plotted, it's exactly this one, x by 2. This is x by 2. This one. This is the original function that we are trying to approximate using the series. Now, if we use two terms in the series, that is n equal to 2, two terms plus, when I say two terms, it means that you have the combination, of course, of cosine and sine, right? That's one term, when k is equal to 1. Because you have A1, B1. Both combined together, that's one term. So you take A1, B1, A2, B2, plus the A0 by 2. That's what gives you S2. Now, S2 is this one in red, sorry, in blue. The graph in blue, you see, this is that approximation. So you see that it is closer to this, to this straight line, y equal to x by 2. It is close to it, but it's not exact because it's an approximation. As you increase the number of terms, you see that from this blue, the next one, S3, is the red one. The red one. Now you see that the red one has more oscillation, meaning that it's getting closer, right? And now we increase further, S4 in green. S4 is the one in green. Now the one in green, you have more terms, you see, and there are also more oscillation, meaning that they are getting closer, 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 and closer. So you see that as you increase the value of n, it will converge and get closer to that straight line. So let us see at that one. Unfortunately, I did not plot it here, but let me show you. Let me check. But it is somewhere anyway. I will show you another case where there are more terms. Unfortunately, I was supposed maybe to plot for n equal to 100 for you to see. But I will show you somewhere here towards the end, something similar. You see this one? You see this one? Yes, because we are using 5 terms. Of course, is it the same function? Maybe not. You see, it's the same function. Here you can see f of x equal to x by 2. So it's the same function. Okay, so it's the same function, but you can see here, if you take, of course, here you are having more terms, but they are not cosine and sine. Here you can see that it's just sine, 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 sine. But that's just to show you that if you have more terms, right? If you increase the number of terms, you see that that straight line, I mean, the polynomials will get closer to the line. You see, if you increase further, you see that it will go exactly, it will converge. That's what you call convergence, you see. This is almost a straight line, almost. You see, that's why we call it approximation. It's not exactly that, but it is closer to it. It's an approximation. Okay, that was just to show you when you talk about Fourier series, what it represents, right? Something like that. If you increase the number of terms, you get closer to that line. All right. Okay, now let us proceed. If you recall what I told you the other day, was it yesterday? Yes. Yesterday when we computed AK, I told you that we could have just set AK to be 0 without computing. This AK, remember that we computed A0 equal to 0 and AK we showed that it was 0. But this was a waste of time, right? Now, how can we know that our AKs will be 0 or BKs are 0? I gave you a hint yesterday. I explained that if the function is odd or even or whatsoever, then some of the coefficient will be 0. So this theorem will give us a precise idea when the expansion will be only in terms of cosine or only in terms of sine. Okay, so that is the theorem, cosine and sine series. If the function we are expanding, f, is an even function and has period 2 pi, of course, if beside f and f prime are piecewise continuous, that's about the convergence, then the Fourier series or the Fourier expansion of f involves only cosine terms, and you can see here. Why? Because the function is even. If the function is even, when you integrate, when you write the, let me show you here. This function f is even, right? Now, this is the expression of bk. Bk, if you recall, is 1 by pi integral from negative pi to pi. And here, what do we have? We have f of x sine kx dx. Here you have an even function. This function is even. And this function is odd. And the product of even and odd gives me what? An odd function. Now, if I integrate an odd function over an interval centered at 0, it is 0. Why? Because I explained to you graphically. If I have an odd function, that an odd function will be symmetric about 0. So meaning that regardless of the shape of the function, let's say this like this one. If, for instance, this is my function, and let's say that this is negative pi, no, sorry, oh, this is pi. And let's say this is negative pi. This integral will be the area below the curve. So if I call this integral A, that area A, this area below the curve is a negative area. This area will be negative. So this will be negative A. Now, if I add these two, which is the sum, because I can split this into 2, I integrate from negative pi to 0, it will give me this. And then from 0 to pi, it will give me that. If I add the 2, cancel out, it gives 0. Okay, this is graphically, but you can write the maths, right? You can write it down. And you see that it will give you 0. So that's why there's no need for you to integrate this. When you know whether the function is even or odd, you know that one of the two will be 0. Okay, in the case where f is even, bk will always be 0. And if f is odd, ak will be 0. And that's the second case here. Oh, where is it? I think, okay, this second case here. If f is an odd function, you can see it here, f, the Fourier expansion of f involves only sine terms, and this is what we have. So meaning that in this case, when f is odd, all the ak's will be 0. For the same reason I already explained. So that is it. Okay, now, I explained this. What I've written here, it's a graphical explanation, but you can do that analytically. Let's try that. Let's try. Let's prove it. We still have 9 minutes. Let's quickly do that. So let me erase this. Okay, so if we use that fact here, you can see that this function is an odd function over an interval center at 0. You can see that this one is centered at 0. So if you integrate the ak's will all be 0. So there will be no need to integrate and write that. Just use the theorem and say it's 0 and compute just this one. All right, now let me go to the theorem. Let me show you that if I have, we are going to do that together. You are doing mathematics, so you should be able to write proofs. So any one of you should be able to write that proof. Should be able to do that. But I will give you hints to do that. I will see if there's, but you should be able to do that. Otherwise, you will never learn. If I write everything for you, you will never learn. Out of experience, your mind is already programmed to sit there and copy, not to make effort to think, which is very bad. All right, so now this is what, let me call it a lemma or whatsoever, but it's part of that theorem. I'm just calling this a lemma. Oh, I promised the other day that I will be giving you, okay, I even wrote it here. I will post that lemma that you'll be using for the assignment. And finally, I didn't do it. Class representative, please. After this class, after the class, remind me. If you don't see anything, class representative. No, you are there. You are listening. Please remind me. Okay. So if f is an odd function. Okay, let's say even first. Even function. And g is an odd function. Say over an interval, negative AA, let me write it this way, where A is positive, right? So it's centered at 0, like this. Then the integral from negative A to A of f of x dx okay, for f which is even, it will be 2 times the integral from 0 to a, f of x dx. Obviously, this is for what? When f is even. You have this. But if f is, g now, here we say g is odd, an odd function. Now for the odd function, from negative a to a, gx dx is 0. So this is the result that is being used to show you that, okay, that one will always be this, it will always be that. AK will always be 0. When you have an even function, when you have an odd function, AK will always be 0. Right? AK will always be 0 when you have an odd function, and BK will always be 0 when you have an even function. Okay, so this is what we have. That this is the statement of our lemma. So what am I going to prove? I can use one of these two and prove it, right? I can prove one of the two. I don't need to prove all of them, but I will give you hints for that because I will not do that for you. You have been doing mathematics over years, so you should be able to think and prove this. So what is the definition of an even function? Let us use the case of an even function. Oh, the odd function. Let me use the odd function in this case of 0. Anyway, this one. There's no time to waste. Okay, so g odd function not only here, it can be odd, just odd function. I don't think we need to specify that it's odd over this. When it's odd, right? Odd over the real line. This one is not really important, but it's fine, right? This is not really necessary. Just odd. When you say odd for any real number, okay. So this implies that for any x in that interval. Oh, sorry. First of all, the negate is still there, right? The negate of that is still there. It has to be there. And g of negative x is equal to negative g of x. This is the key, and this is what we'll be using. This is the definition. Okay, so that's the definition. Now, what do we want to prove? We want to prove this, right? We want to prove. So now, when you write this integral from this to that, dx, you have this. You want to show that this integral is 0. Right. You want to show that this integral is 0. Okay, so you can use a change of variable. You can use a change of variable for this one. Right? So you can write that this is what? You can split this into two. You can say it's the integral from negative a to 0 gx dx plus the integral from 0 to a okay. So from that, you can just use this one and apply the change of variable. So you can use this one You can use this interval. You can use this. And apply the change of variable, for instance, y equal to negative x. And use this fact. So if you use that, this will become negative, this one, and they will cancel out. Okay, so that's what you need to do. Okay, that is it. Please do that. And you can do something similar for f, and then you get the result. Is that clear for all of you? That's all, just a change of variable, and that is it. Okay, we'll stop here for today. We have already exceeded by 1 minute. I'm sure you have a class after this. Thank you so much for your kind attention. God bless you and see you. Not tomorrow, because tomorrow there is no class. See you on Friday. Thank you. Bye-bye.